Pleasant good morning to everyone. Thank you, Mr. Chairman, for both the introduction and creating such a strong rationale for improving oil recovery in Trinidad and Tobago. This morning, I'm here to talk about a closer look at CO2 emissions in Trinidad and Tobago, and in doing that, pay particular attention to our sources, quantities, and properties. Now that we know that Trinidad and Tobago should aggressively pursue improve oil recovery, and now that we've outlined that CO2 EOR is one of the ideal technology, or can be one of the ideal technology for in doing that, we're now going to look at the very important ingredient for that technology, the CO2 itself. And I would just like to reiterate what Mr. Abdul said about embracing an opportunity. We have two major issues. There are many issues with respect to the energy sector, and we're addressing those, but there are two major issues. One is the decline in productivity of our hydrocarbons, and the other is the rise in emissions, greenhouse gas emissions. If we can find a way to marry both issues and embrace the opportunity that lies therein, it's a win-win situation, it's a sustainable approach, and that really is the conceptualized idea behind CO2 EOR in Trinidad and Tobago and this talk. I would just like to recognize the inputs of Ms. Sophia Jones and Ms. Rina Rampasad to the talk today. There are many things I can say on this topic. In the interest of time, I'll keep it very focused. I look at some methodologies for conducting greenhouse gas inventories. It's very important that we pay attention to the methodologies so that we can adhere to international best practices when we're computing our greenhouse gas inventories. The link between CO2 and greenhouse gas, as you all know, CO2 is a greenhouse gas. And if we want to quantify how much CO2 we have, we need to follow the methodologies that are out there that are tried, tested, and proven in computing greenhouse gases. So I'll introduce you briefly to those methodologies. We'll then be presenting some results for Trinidad and Tobago latest greenhouse gas inventory, right here on the stage, 2015 emissions. UTT, as an institute, periodically always publish figures with respect to greenhouse gas emissions in Trinidad and Tobago. And prior to today's talk, the last figures that we made up available to the public were the 2010 figures. We've since updated that to include 2011 onwards to 2015. This morning, I will give you a snapshot of the 2015 results. And in so doing, I will bring the presentation to life. We will see the sources of CO2 for CO2 EOR, possible sources. We'd have an idea of the quantities we're talking about. We talk briefly about the properties, and then we conclude. And in concluding, we'll actually exemplify what these quantities mean in the context of enhancing oil recovery. This is the academic in me, definitions. What is a greenhouse gas inventory? Estimates of emissions of greenhouse gases occurring from given sources within a defined region for a specific period of time. You would basically see all of these ingredients as we look at our latest results. We must be very careful. We must be very, very careful when we're talking about greenhouse gas inventories and CO2 emissions. All greenhouse gas inventories are reported in a unit known as CO2 equivalent. It's an account of all your greenhouse gases, and there can be many different greenhouse gases. This table just shows some, but it's all brought to a base unit of CO2 equivalent. And that base unit is found based on the global warming potential of these greenhouse gases. A greenhouse gas has this ability to trap heat due to its dipole effect. Based on the potential to trap that heat, over a given time horizon, we have a global warming potential assigned. CO2 was assigned that GWP of 1. So it was used as a datum or basis whereby other greenhouse gases could be weighted. Why am I making this point? When you hear a particular nation emits 50 million metric tons of CO2 equivalent per annum, note that 50 million metric tons is not all CO2. As we present our inventory results, we would distinguish what are our CO2 emissions from amongst the CO2 equivalent that we would report. Now, there are two ways to perform this measurement. One of the ways is via direct measurement, where you have some instrument that directly measures your greenhouse gas or your CO2 as it may be. That is not always practical. Sometimes these emissions occur from scattered sources. Sometimes these emissions occur at different temperatures and pressures and localities that are difficult to measure directly. So when it comes to national greenhouse gas inventories, the approach utilizes really an indirect approach. This is worldwide. It's more practical to do so, and what the indirect approach does, it utilizes correlations to estimate your emissions. Some correlations for the chemists amongst us can be stoichiometric balances. Some correlations are activity data, and we'll show you some examples as we go later on. So our methodology applied, as you would have guessed, would be the indirect approach. And even within that approach, there are two ways in which you can do it. One way is a bottoms-up model, and the other way is top-down model. A bottoms-up model, via the indirect approach, is that way in which the source emitters compute their emissions indirectly and submit these values to some central regulatory body. Trinidad, it can be the EMA. That approach has a lot of merits, but as you would imagine, that approach requires some level of monitoring, reporting, and verification. We cannot just take the figures submitted by the source emitters for granted. We have to find some way of monitoring this and verifying if it's accurate. Trinidad and Tobago is in the process of developing that MRV system. So since that MRV system is not yet fully developed, the bottoms-up approach for Trinidad and Tobago is not advisable. So we move to the top-down approach. This approach is simply getting our input data, fuel usage, the drivers of emissions, and using correlations to compute the emissions. So in a nutshell, what did we use? We used the indirect approach via top-down model. And even there, the different levels of estimation. 3 tiers, as outlined by IPCC, latest methodology, 2006. These tiers really refer to the degree level of accuracy, the varying levels of accuracy. A tier 1, simplest method, but it can be the least accurate. It's the least data intensive, but also the least accurate. A tier 1 basically use default emission factors to calculate your emissions. A tier 2 jumped into the results very quickly there. A tier 2 uses country-specific emission factors. And the tier 3 approach utilizes, in addition to country-specific emission factors, the varying technologies are taken into consideration. So you go more in depth, as you would imagine, a lot more data intensive, but a lot more accurate. Our inventory utilizes a hybrid of all of these. In some sectors, we utilize the Tier 1 approach. In some very important sectors, we tried as far as possible to use our Tier 3 approach. So that's a nutshell of the methodology. And we start again into the results for Trinidad and Tobago here. In the year 2015, 45 million tons of greenhouse gas emissions, or CO2 equivalent emissions, occurred in Trinidad and Tobago. More importantly, more than 80% of that emanated from these two sectors, the petrochemical and power generation sector. We had some other sectors that contributed, transport, for instance, 9%. But look at those two big sectors, our petrochemical and power generation sector. This chart, in my opinion, gives us a very good basis for managing our emissions. What this chart is really saying is that most of our emissions in Trinidad and Tobago comes from large point sources rather than mobile scattered sources. And theoretically, that's easier to manage. Let's look at these two big sectors in a little more detail. When we look at the petrochemical sector, we see that within that sectors, these two subsectors, that is, ammonia and methanol synthesis, contribute for over 80% of the emissions therein. So this is also something that you need to pay attention to and understand that if you really want to manage and mitigate your emissions at any significant levels, these are the sources that you would want to pay some more attention to. The others, no doubt, you can also implement measures therein, but these are the major sectors, ammonia and methanol. We'll talk a lot more about ammonia later on. And as before, these two sectors subsectors within the petrochemical sector account for more than 80% of the greenhouse gas emissions. Let's look at the power sector a bit. And this is what I refer to as the triple 80 effect. You're seeing the third 80% here. This symptom of Trinidad and Tobago greenhouse gas emissions did not change since 2010. What symptom am I referring to? The triple 80 effect. The triple 80 effect is simply of all our emissions in 2010 and even in 2015, over 80% emanated from the petrochemical and power sector. Within the petrochemical sector, over 80% emanated from methanol and ammonia. And within the power sector, over 80% emanated from industrial use of power. My friends at TNTech always call me up on this slide, so I just want to elaborate for their benefit a bit. This takes into consideration power generated by Atlantic as well. If you just take into consideration the power from the TNTech grid, this percentage is actually closer to 70%. And that is what TNTech knows. But if you actually take all power in Trinidad and Tobago into consideration, integrating Atlantic, over 80% is used in the industrial sector. All of these have serious implications from a CO2 EOR perspective, which I'll talk about later on. These charts, though, have not been updated. These are still 2010. Trinidad and Tobago, based on our emission levels in 2010, incidentally, which was 53 million metric tons. So since 2010 to 2015, we've decreased. We went from 53 million metric tons to 45 million metric tons, as reported in my first pie chart. That decrease is largely attributed to the decrease in gas supply, and hence gas consumption. In 2010, we were ranked second in the world in terms of emissions per capita. In 2015, we're still ranked second in the world. The only change is that Qatar went up to 44 on that quotient. We dropped a bit to 36. As I said, the numerator dropped, that is the amount of emissions, right? And the per capita increased slightly for Trinidad, the population that is. So we dropped a bit, but we're still second. In terms of emissions per unit GDP, in 2010 we were second. In 2015, we're still second. The numbers did not change much with respect to emissions per GDP, the quotient value. Every time I talk about Trinidad and Tobago greenhouse gas emissions, against different backdrops, I always invoke this slide. This slide shows Trinidad and Tobago emissions, our 2015 case, versus the world average. The latest I got was 2006 for the world average, but it didn't change much. Why do I invoke this slide? I like it to be echoed in the room that Trinidad and Tobago is very unique. We must approach mitigation measures taking that uniqueness into consideration. What worked in other places may not necessarily be as relevant here. Let me elaborate. Firstly, our absolute emissions level, 45, will a lot more. So on an absolute basis, we are insignificant producer of greenhouse gas emissions. You've seen before, we're second in the world per capita and per GDP. But on absolute basis, we're very insignificant, accounting for less than 0.1% of total global emissions. These are the figures I would like you to pay attention to. The emissions from our power generation sector in Trinidad account for 27% of our total emissions. The world average is 41%. The emissions from our transport sector account for 9%. The world average is 22%. Why? Because of this sector. The emissions from our petrochemical and manufacturing sector account for 56%, whereas the world average is 22%. So because we are so industrialized, that's the reason why these other two sectors, relative to the petrochemical sector, account for far less than the world average. But that's not the only unique pattern. This is another one. A large bit of this, as demonstrated in one of my slides before, emanate from the ammonia synthesis. So in addition to these unique patterns, in Trinidad and Tobago, owing to a relatively large ammonia sector, a lot of the emissions therein of a relatively pure CO2 composition. We'll talk about percentages in a bit. But a lot of the emissions in Trinidad and Tobago that emanate from that sector are of relatively pure compositions. That is what we refer to as one of the low-hanging fruit for CO2 EOR. When you want to use CO2 for enhanced oil recovery, from a fluid interaction point of view, it may not be that important. Some studies are indicating that in terms of your CO2 purity. But remember, you need to transport the CO2. You need to compress the CO2. So if the CO2 composition is small, you're actually compressing and transporting other gases and paying for that. That would negatively affect your economics. So obviously the pure sources are the low-hanging fruits. So let's talk a bit about this pure source in Trinidad and Tobago in a little more detail. These are just some slides for ammonia, estimating the emissions and ammonia synthesis in Trinidad and Tobago, because in the interest of time, we can't show everything. Our ammonia facilities use natural gas. And the natural gas that goes to our ammonia facilities in Trinidad are used for two main purposes. One is to produce heat, and the other is that natural gas is actually used as a feedstock, where the hydrogen component of the natural gas is needed for the reaction to synthesize ammonia. So of all the natural gas going to the ammonia plant, a certain percentage goes to produce heat, and a certain percentage goes as a feedstock. The percentage that goes to produce heat, we've utilized this simple tier 1 approach to quantify the volumes of CO2, not CO2 equivalent, volumes of CO2 emanating from ammonia production. And you realize for this we needed fuel consumption data. And the Ministry of Energy website has fuel consumption data. And very quickly we were able to compute the emissions in the ammonia synthesis plants in Trinidad and Tobago from that heat usage of natural gas. So it's a lot. It's about 5 million metric tons per annum, close to 6 in fact. But because of the process that it goes through, which is really combustion, when we talk about purity levels, though it's a lot, the percentage composition of CO2 is just about 9 to 15%. But if you look at the other use, that is where it's used as a feedstock, we use this hybrid approach to estimate the emissions therein. It looks very easy, one simple equation, but it's very data intensive. In the interest of time, I won't elaborate further. You can get the slides. We got the data. That's just to show you Ministry of Energy again. We got the data. And we got the emissions from the process side. From the heat side was between 5 and 6 million metric tons per annum. On the process side, it's as much as 8 and recently 8.3 million metric tons per annum. We are illustrating figures for 2014 as well here. And this is the important statement. These have purity levels of over 95% CO2 by volume. We have a very good idea what are the impurities, but it's not really relevant to the discussion at hand. Depending on what you want to use the CO2 for, you may want to know what the impurities are and remove the impurities. In fact, some of this is already used. So these are the pure volumes, but these are not the volumes that are available to us. Because some of these are already used in subsequent industries. Some of this is used for methanol manufacture. Some is used in the food and beverage industry, and what have you. And depending on the usage, I said, you may want to further purify the CO2 levels beyond what you have emanating from the plant. So that's one of the low-hanging fruit. But perhaps, based on Mr. Abda's talk, the lowest hanging fruit in the very short term lies with Atlantic. Of all the natural gas that goes to that facility in Point Fortin, about 9% of that is used to run the compressors, to compress that natural gas into a liquid form for export. And when I mean 9% is used to run the compressors, basically 9% is used for them to generate their own power. And that is the power integrated in my third pie chart. And therefore, the emissions resulting from that are much like the heat usage of natural gas that I demonstrated in the ammonia plants. It's not that pure. So that's the first thing you need to pay attention to. When you hear about the emissions emanating from Atlantic, it may be a lot,